what we are talking about by the end. There are natural places where I'll pause and ask for questions. I'll try to aim for, say,
recording in progress,
45 to 50 minutes, so that we have 10 minutes of open-ended questions for everyone here. And then we can go from there. Yeah. Right. Should I try to share screen, perhaps while you're waiting?
Yeah, sure.
Let me know if you see the video playing and everything correctly.
Yeah, it's playing.
Wonderful. Yeah, so we'll wait here while we start.
Right, so I think we can start right now. Good morning, everyone. We are really overwhelmed to have with us Dr. Animesh Garg for our next tech talk. Dr. Animesh Garg works as an assistant professor of computer science, especially robotics in University of Toronto, and as senior research scientist at Nvidia Robotics Lab. Dr. Garg is a wizard when it comes to generalized autonomy and mobile manipulation. Personally, I'm a big fan of his work in multi-agent reinforcement learning and his work in amalgamation of computer vision with robot manipulation. But to make this tech talk a little more generalized, Dr. Garg has agreed to speak on robot manipulation and simulation in industrial robotics. I guess I can't stop myself voluntarily from praising his works and listing them, but also in the same time, I don't want all the participants over here to curse me. So without any further ado, I think I would like to warmly welcome Dr. Animesh Garg and would request him to please take the podium.
Thank you so much. Thank you, Surya. And thank you to all of the organizers of Takshak at ISM. And all of you guys are doing wonderful work. And I'm really pleased that you guys have thought of me to be speaking here today. For all of you who do not know me, I am Animesh. I am currently on the faculty of University of Toronto and Vector Institute. And I'm also a researcher at Nvidia. And mainly, I enjoy my time working on algorithmic foundations of intelligence, particularly embodied intelligence for robot learning. And a lot of the focus that I have is thinking about what sort of algorithms would make this general purpose robot intelligence possible in the future. And as a joke, you can really think about, as a researcher in robotics, it is my personal dream to think about what would it take to build a system that would work out of the box, very much like your phone works out of the box. You just buy it and everything works out of the box, magic. What would it take for us to do to get something similar, let's say for a robot, maybe a household robot, right? And what I'm going to talk about today is to give you a few examples of what we have been up to in the last few years and also broader picture of what are open problems. Again, this is not supposed to be what I would say a tutorial, but at the same time, feel free to ask any and everything. No question is stupid. Just be very, very clear. So nothing is too simple. No question is too stupid. Feel free to ask. Feel free to interrupt. The more this is a conversation, the more fun this will be. Okay, so let's get started. So what do we want? We want a robot that can do everything. What do we mean by everything? Well, we can say that what we mean by everything is maybe, let's say, household tasks. I want my robot to clean. I want my robot to vacuum, sweep, mop, maybe cook, maybe do some laundry. A bunch of you live in dorms. But all of this is what you would say lab stuff, right? It, of course, works in lab stuff. But when you have a robot that should probably work in more complex domains, right? Maybe your home, my home, your mom's home. So it needs to work with new objects, new tools, new scenes, maybe solve more harder tasks, maybe even harder tasks, maybe things like you haven't done your laundry in 2 weeks. Happens all the time. Happened to me. What happens in that case? You have very, very dirty dishes because you spent last weekend party. That's still a possibility. So all of that is something that our robots or these agents need to be able to handle. And it's not clear how, actually. And now, of course, I'm giving you examples of what I call kitchen, and because everybody gets kitchen, but it's not really limited to kitchen, right? It's something that goes beyond to any sorts of industry, really any sort of physical work, if you will, right? And it's not that we don't have hardware. I wouldn't say we have the final hardware, but we do have a lot of impressive hardware. You may have seen these sort of interesting robot dancing clips in the last few months or so. These are, of course, clips from our friends at Boston Dynamics. And they've built what I would call impressive hardware that can do very, very complex things. And it's really a feat of engineering and science, to be very honest. And I'd claim no work here. But what is interesting is when you take these expressive and really capable physical systems and ask them to do realistic stuff, they fail rather spectacularly. And it's not clear why. Perhaps sometimes it's perception, sometimes it's planning, sometimes it's just that the world is not choreographed. The dances were choreographed, but the world is not. So building real robots that work in real world is, well, really, really hard. So what is the problem? And this is the problem that I call algorithmic generalization, in the sense that we have a lot of hardware, but it's not clear how do we generalize to objects, scenes, semantics, and perhaps task goals. So what is needed? The big picture idea here is that we want to build these intelligent companions that can extend ourselves, really. It's not that we are building, I don't know, Terminator, but what we are really building is better tools of tomorrow. And what do we need for better tools of tomorrow? One, there's a mechanism where we can tell the tool what to do. Right? So you should be able to tell the system, you need to assemble a chair. You need to wash my clothes. You need to, I don't know, make me an omelet. And then the system, of course, needs to be able to do that in that particular setting, but also perhaps generalize so that you don't have to teach it every single thing, every single time. Right? So if you told it how to pour water from one cup to another cup, you should not be able to, you should not need to do this yet again when the cup of the color of the cup changed or the shape of the cup changed or so on and so forth. Right? Now, of course, one might say that, oh, but if you're going to be teaching these systems, teaching must be very easy. What is there? Copying is easy, of course. Let's think of a very simple example. Let's say a mom is trying to teach her kids simply to sweep the garden, nothing else, something very, very simple. Sweep the leaves of the garden. A 2-year-old really doesn't do anything. They just get the mop and really shake it around, trying to copy the mom. Nothing happens. This is what you can think of like imitative babbling. They're trying to copy the motion without really understanding what it is about. Then as they grow up, I don't know. Yeah, as they grow up, something weird happens. What happens here is that they try to figure out what is, let's say, the skills, or what is the sequence of skills that needs to happen here. And then finally, as they grow up even more, they figure out that it's really the task that matters and really not the motion. Right? So causality pops in, where like the whole point of this effort is to rake leaves and not really wave the broom. Right? So this is the key question in robotics. Right? Even if you can specify the task, at what level should you understand the task, and how should you copy if it's clear? It's not easy to copy, as many of you may know. Right? I think someone was trying to use the screen for annotation. Maybe we can clear annotation, let's say. Okay, cool. Okay, so going forward, what is sort of, if you look at a lot of the progress in the last few years in computer vision, natural language, you could argue that it is built on a lot of new and interesting data sets. And as the size of the data sets have grown, the performance has correspondingly improved. You can really think of the pillars of modern machine learning that you've seen in the last 5 to 6 years is the use of large structured models. Deep learning can be thought of as a version of these structured models, large data sets, and finally the availability of distributed compute. So you can really think that the fact that all three of them exist, you start seeing a lot of progress in the space. Without any one of them, you would say that this would not be possible. Now, interestingly, robotics is slightly different. Different how? Well, in the sense that it is allowed to break these assumptions. The world is embodied. You are actually in the world. You can find creative solutions that are very hard to label. So dataset creation is hard. You are actually interacting through dexterity. It really essentially breaks all of these assumptions, right? The models in robotics or even reinforcement learning are not very large. Data sets are very rarely available and definitely not IID, if at all. And finally, robotics is not yet at a point where we are talking about distributed deployment the same way we are thinking about, let's say, natural language processing. You have phones have voice recognition. The fact that voice recognition works is because these models were trained on large-scale compute, and your phone is live connected to a server where basically this sort of inference is running, right? The same may not be possible for robotics. At least people are making progress, but it's not something that exists. So this is what brings us to what we need to do in terms of research. And hopefully some of you may be interested in this. To build general purpose robotic intelligence, I would argue you need to improve three things, and these are independent and equally important pillars. It's not that one is less important. One, you need to think about what sort of algorithms or algorithmic structure would be required. We cannot be using simple, old school machine learning algorithms just translated to robotics. Two, can we use more data through newer concepts in machine learning, such as causality? And finally, we are, after all, in the process or in the business of building real robots. So essentially, you'll have to think about what will it take to deploy these systems? What sort of challenges will present themselves as you build a practical system that is deployed in the world? Okay. So what I'm going to give you today is basically examples of all three of them. Okay. So let's get started with the first part, which would be structure. Right? So what is the question? The question is very simple. Machine learning over the years recognized that correct learning biases are required to suit the needs of the domains. What does that mean? Well, we started with computer vision with MLPs. We have ideas of attention mechanisms. We have thinking. We have models which can do transfer learning, contrastive learning, and whatnot, right? But when we talk about intelligence, one could argue that essentially intelligence is not to solve data sets, but actually it's built for interaction, real live agents. But a lot of these models that exist do not solve this embodied decision-making problem in the same way. So let's continue. So what gives? So let's do a very simple refresher here. Many of you may not be aware, many of you may be. Feel free to ask questions here. A lot of the times when we think about decision making, particularly in robot learning or reinforcement learning, we use this concept of Markov decision process. What is a Markov decision process? It's a very simple decision making framework to model decision making problems, in the sense that think of the blue box as an agent which is observing something. Let's say it's a robot, right? So it is seeing some sort of camera. It has some sort of agent joint encoder, so it can understand what the joint angles are. Then the agent itself can be thought of as some decision-making algorithm or rule. Let's say it looks at a state and decides whether to go left or right, right? And then it outputs something. Let's say it's an action. The action can be anything. If it's a car, it may be go forward, backward, stop, brake, left, right. Or for a robot, it can be, let's say, torques, how much force to apply at each joint. And then the environment is basically the world that takes your action, world moves forward in time and tells you what is the utility of your action. This utility is called reward. This loop can iterate forever. And this framework is called a Markov decision process. And this is what you would say a core object that is used in reinforcement learning. The solution to this problem is the whole quest of reinforcement learning, if you will. Okay? So this is something that I will use multiple times in today's framework. So if you have any questions about what this is, feel free to ask, as I said. Okay. Absolutely. Go ahead, Piyush.
Yeah, sir. I was wondering, like, I have been working with manipulators, and I have used this vision system sort of for color sorting purpose using a 6-wave manipulator. Okay. But sir, I'm confused, like how, which platform do I have to use for applying of reinforcement learning using camera vision? Because sometimes it happens that there is a calibration problem, that the plane is inclined, or there might be other issues also. So I was like, this was a quite good aspect which I have seen. How can I make data set out of the working model of my manipulators and then put it through so that the calibration problem is eliminated, and with time things do improve and optimize.
Well, it'd be very hard for me to argue which platform. I think it will be for you to decide what platform is available to you, and what sort of resources do you have for something like that. A lot of the problems that you are looking at you could start with the simulator itself, which would require much less compute, so that you can test out a lot of your framework, and then you can go from there.
Sir, any suggestions, like top 3 sort of thing? So I'm just a beginner in AI or robotics.
I really don't know what sort of arms are available to you. A lot of the arms we use may or may not be available. I would strongly suggest, if you're starting out in robot learning, start out with decent simulators. A lot of the skills that you will learn from those simulators will transfer over.
Okay, thank you, sir.
By the way, Surya, can you help me moderate questions? So what would be very good for everyone who is here is to put your hand up. I think Zoom allows you to do that. And then Surya can call out people in some sort of sequence, so that people don't feel that they can't ask questions. Okay?
Yes.
Okay, so let's carry on. So the first question that we were trying to ask was, how can better state or action representations lead to generalization in robotics? What does this mean? Okay, so let's think about a very simple task. The task is to, open doors. So if people are opening doors, even if they're trying to open doors that are new doors, they are not trying to yank the door in up, down, left or right direction. They know that doors open in certain manner, and they're only even trying to open those doors in those directions, right? So you're not trying to go to a new door or someone's home and you're like yanking the door up or down. It just doesn't work. It's not common sense. Well, you think about robots. Robots are practically just doing that, right? Sometimes it works, sometimes, it doesn't work. Right? So what happens there? So what can we do? one way to argue about these sort of tasks is it's not necessarily just opening doors. Any sort of task, you could argue that this exploration, even if you don't know what to do in this new environment, could be limited to only certain subset of directions of what you could do in that place, right? So if you're trying to wipe a cabinet or let's say a table, you don't try everything like banging on the table. That's just stupid. You just try to wipe the table surface, right? And maybe you vary the force on the surface, but you're not doing this. Nobody does this. It's weird. So how do we have systems achieve this kind of behavior, right? How do we achieve this sort of what you would say common sense? First of all, discover this common sense, and then, well, ideally learn to figure out what are the right variables in different tasks. So one way to do this can be, well, let's use reinforcement learning. But often what happens with reinforcement learning is exactly the kind of behavior I mentioned. You try to sort of wipe the table and the robot learns to bang the table oftentimes. The other solution can be, well, I'll code it up. Of course you can code it up, but the problem is you need to code it up. So which means that a very valuable engineer's time goes into coding this up, and it may take multiple days. And even then, it will work only in one case. And then what happens is something changes, and then you have to go in again. So how do we solve this problem? Can we do some sort of best of both worlds? So that's what we thought. Maybe we thought first, maybe we can use some sort of best of both worlds idea where we can say, we can learn a policy where the policy is taking in some sort of image observations. Let's think of observations as O. And then the output of that policy can be given to a robot model. So it's like best of both worlds in the sense that I'm still learning, but I'm outputting it to something where I'm using my prior knowledge about my robot. So what this does is you basically say something like this. I know a lot about my robot. Let me choose the choice of action space, not in terms of, let's say, what my arm does, but what my hand does. So where my hand is. So think of it like this, that if my hand was completely floating in space without knowing what the arm was doing, then I'll still be able to open the door, right? Because when I'm interacting with the door, the only thing that matters is this hand. Everything else is free. So I can solve for my hand given the position of this arm, right? And the other thing is, I will allow the policy, the learned policy, to figure out how stiff does it need to be in different stages of the task. What does this mean? This means that when you're, let's say, reaching for the handle of the door, you are not stiff in any direction. It's like your hand is essentially loose. Like, think of like doing this completely blind, right? When you're in the dark, right? As soon as you touch the handle and you grab the handle, then you become stiff in certain directions, in inward or outward directions, or upward or downward directions, while you're very less stiff in inward or outward directions. So for example, you can move here, but you will not move here or here. Okay? So everybody with me, right? What this is essentially saying is, you're not modeling the environment explicitly. So you're not saying that this particular door needs to be open. You will learn which door to open. But you're basically saying that everything that I know about the robot, I know. So I don't need to learn this anymore, right? So it's best of both worlds in that sense. Now, what does it buy us? Well, I can directly jump to what does it buy us. I can now, yes, go ahead, questions.
I guess Aman Kanoji has a question.
Aman, go ahead.
Yes, I got the answer in the next slide when they said turn the next slide. So I want to ask that we can code if we have the simple task. Why are we we want lots of data to train the model for a simple task? So why can't we code just to don't get that lots of data from any source?
Absolutely, that's a completely valid question, right? Let's assume that Aman says, I can code up opening a door very easily. Why do I need to bother getting so much data and like going through this whole process of learning? Well, think about this, right? The same algorithm does both wiping and learning. So I don't know how many of you are computer science or electrical engineers. think of it like this. Do you know how macros are written? Do you know what a macro is? I don't know how many of you know what macros are. So macros are basically, think of it like this, that think of a very simple example. Forget about macros. Let me give even a simple example. Let's say you're trying to play, I don't know, cricket or tennis. Like, one way to think about this is, why do you need to practice? One argument for practicing is, it provides you a lot of data so that when it is match time, you don't have to think. Like, you just know instinctively what to do. That is what is the equivalent of learning, right? Now, Aman is saying, oh, but I can do this sort of instinctive thing. I can code this up so that like I know what to do when a particular situation happens, right? When it's a short ball versus a full ball, right? Now, you can really think about this as you can do this for every task separately. So you can do this for the door, and you can do this for the wiping, and you can do this for pouring. And think of all the tasks you can do and how many times you need to do this. Or you could write a single algorithm that will do this for you, all of it. Right? So the whole point is to write a single algorithm that will essentially do all of it. Think of it like this. When the data scales, it's much easier and much lower amount of engineering time is needed to do this. So that's the whole, let's say, quest of learning to begin with. Write a general purpose algorithm that will work for everything. Not all at once. You'll still need to do separately. It's not like a single algorithm wins them all kind of argument. But the same thing works for all sorts of interesting tasks, rather than writing separate controllers hardwired for different tasks. Piyush, go ahead. Piyush?
Hello. Yes, sir. Sir, suppose when we apply our algorithm in our on a robot, it works in a certain environment. It takes environment factors as a consideration, right? So if that environment changes with like, that can be a subtle change, or that can be a generic or large change, then does the robot go again to the zero level, or will it progress itself after that? Like, for example, in this Panda robot, it is like, I think it is erasing whatever the human is writing on the board. So if there is a particular Z value that has to make contact with the end effector to the board, Z axis value, right? So if I just decrease or increase that Z, it might also damage the robot. But so in that case, will the robot automatically understand that it has to take into consideration of Z values? Or like if my board is inclined, that might also play a different.
If you notice carefully, the table goes up and down during the course of the video, and you don't have to code it up.
Okay, that's good. Yes.
Right? So that's precisely the kind of algorithms we're trying to create, so that we don't have to code this up. Right? You can turn the table if you want. You can put the table up or down. It's fine. And you don't have to even measure exactly what is the table like depth is or something. This is something that is learned.
So one more question on the chat section. It says that we have seen that ML algorithms work vastly in a more robust way in a higher latent dimension. Then why do we go for a small latent dimensions in reinforcement learning, or in the previous slide that you have shown?
Primarily because of the data efficiency. So if you have millions of data points, that sort of algorithm could be easy to learn, but often reinforcement learning is slightly more, let's say, data hungry, and let's say compared to your data sets where data is essentially pre-baked, you don't have this data a priori with you. Okay?
Sure,
okay.
I guess.
Okay, so let's continue. So what I showed you is that this sort of choice of action space helps you build algorithms for manipulators. But this idea is not limited to manipulators. I can do the same for walking robots. So think of walking robots, and instead of trying to solve the walking robot for every leg, you can really think of the robot as flying potato. So it's just flying through space. The only thing you have to think about this is what happens to the potato. Once the potato figures out what needs to do, then the legs and all of the details can be filled in later, right? So and those details are actually like the forces that are applied to every joint, every leg, and every leg that makes contact on the ground, and so on and so forth. But the interesting part is, in doing so, you can do interesting stuff. You can teach a robot to walk. Okay. Now, if you had pure RL or reinforcement learning and you taught the robot to walk and the leg flipped somehow, or there was a change in morphology, the robot completely flips out. There's no way to figure this out, of course. But interestingly, the same policy that you train with can now also work on testing on a slightly different robot with flipped legs. Why? Because we are thinking of robots as potatoes. So it doesn't matter if the legs are flipped. I'm able to adapt on the fly. What does this do? This also allows me to transfer. So I can train on simulation and I can then put this system or put the same policy on a real robot. And the same thing works magically without me doing a lot of data collection on the real robot, which could be very expensive, very time consuming. Simulation is cheaper, right? Okay. So far, we talked about this idea that, we need to define what action space is. And then if I know the right action space, I can use it for learning to do these tasks. But what if I told you we are now trying to go one more level of learning up, in the sense that I want to learn this action space itself? What does this mean? From a learning perspective, what this means is I have a data set, and now I'm going to train a model. Again, don't worry about the details of the model or what each of these blocks mean. But what I'm going to train a model essentially to replace the action space that could be the robot, let's say joints, with a learned action space, A hat. And what is this learned action space doing? It's basically allowing you to control. Think of it like this. When you're playing a video game, you don't really control the full controller through each of your control mapping, right? So if you're playing, let's say, soccer or tennis or any sort of video game, right? You're not controlling with controlling each joint, but you're controlling with a very simple controller, move forward or move backward. And what if we could learn directly what that controller should be? And this is what this system is doing, right? So then what does that do? It allows us to go back to those tasks that we were looking at, basically, let's say, opening doors and closing doors. And now we can compare the performance of pure RL or reinforcement learning with this learned model. Why is this learned model interesting? This learned model is interesting because it discovers that, for example, doors only open in one direction. So even yanking them is only in that direction is useful. Otherwise, it's not very useful. And this shows up in numbers, in the sense that now with this learned action space, the system can be much, much fast in learning to do the same task. In fact, you could argue that it could also generalize to new tasks, in the sense that maybe all previous doors it was trying to open was 30 degrees, and now the new door needs to be opened to 120 degrees. It works. Even more interestingly, when you don't even have the data, you can learn this correct action space, so every future task will be fast. And same idea actually also works in wiping, right? So this was an example. So if you learn to do the wiping, maybe of circles or straight lines, and then you ask the system to wipe things that maybe you have not seen, patterns that you have not seen, but now what you see on the rightmost is the algorithm that we have learned to do this. But the third one, which is the SSE baseline, it really doesn't. Why? Because it has only learned or memorized only one task, while it doesn't generalize when, let's say, the pattern changes. Okay? And then finally, as I was saying, why bother just using reinforcement learning? You can directly use it for human control. So we did exactly that. We collected some data and we learned an action space which would allow humans to control these robots with very low dimensional controller, in the sense that a simple joystick up-down is able to control this complex robot. Only one dimension, right? So only a joystick is used to control, no buttons, nothing, right? And then when people were asked to complete these sort of pick and place tasks, people found that completing or controlling complex robots was 5 times as fast with these systems. So far what I've told you about is this idea that if you choose the output space intelligently, you can do much better. What about input space? So let's consider this task of multi-finger manipulation. What is multi-finger manipulation? Multi-finger manipulation is this task where in a single hand, you're trying to manipulate an object in place, right? One could argue that this is really hard. This is actually very complicated, right? So what people have done is created these robots, which are 3-fingered instead of 5, to study exactly the same problem. And in each of these tasks, the idea is to put the object in a certain pose. So you have to learn to do this. Now, of course, you can try to code things up, but coding things up is very slow or very hard. OpenAI, a few years ago, showed that they could attempt something similar with a very expensive setup, which required a lot of compute to a point where it was basically out of reach of everyone. It requires centuries worth of compute of the order of millions of dollars, if not more. Right? So now the idea was, can we use this real robot challenge, which allows access to remote simulators, remote robots, and combination with large-scale simulation to achieve interesting results? So in this case, what we found was, again, naive reinforcement learning may not work, but if you change the representation of the world, what is the representation of the world? You are trying to match the position of the cube. Now, how would you represent the cube? You could say that I can represent the cube as a 6 vector in space, right? Which is what we call pose. Now we need to match pose, current pose with final pose. Now, this representation doesn't really lend itself to easy optimization. However, if you think about this, you can optimize the position if we do simple 2D matching, which is basically saying that there are 8 points and each point needs to go to a certain location. If that is how we represent the world, then optimization space becomes much easier to train this. How does this training work? This training works with more, let's say, conventional reinforcement learning algorithms in a deep learning setup, purely in simulation. And we also add what is called domain randomization in simulation. So what are we doing here? What we are doing here is we are adding randomization in simulation for, let's say, the mass of the cube, the shape of the cube, maybe the amount of force you can apply on the cube, maybe the friction on the cube. In doing so, you're making the controller or the policy learn a robust policy that will also work on the real robot without tuning. Why? Because hopefully the real world is also something slightly different, but not far too different. We don't know what exactly is the friction in the real world, but if I've trained to handle a large variety of friction, perhaps I'll also be able to handle real world. Now, if I think about this, what I can do is I can train this for very large compute time steps, billions. This is something that is 3 orders of magnitude larger than most other people. But the interesting thing is I can do this all on a single GPU, on a single computer in a single day. So we are basically doing what was done in centuries on a large scale cluster, basically on a single computer. Right? So the net result of these techniques is a policy which is able to learn this task purely in simulation and gives good performance on this 6 degree of freedom reposing task. Right? And notice that it gets to the goal very quickly, but after that, it spends all of its time to make sure that it can maintain the pose. Now, it's not that it's just learning something very simple. It's learning rather complex strategies, right? So it's learning to do initial grasping. It's learning to flick the object, drop the object, and then grasp it again, and so on. And now, more interestingly, all of this, when we put this on the real robot, works directly on the real robot, which is both sort of surprising, but at the same time so exciting. That I can train completely in simulation, and with ingenious and smart tricks, I can directly go to the real robot. Notice this real robot is not even with us. It's basically completely remote, and we are just giving it policies to run as if this was running a model on your phone. Which is why this result is very exciting, that you can do remote robot deployment with large-scale simulation trained properly. Okay. So far, I gave you examples of how choice of structure, both in input and output, or representations of input and output, can help robot learning. In some cases, it can even speed up robot learning much more. Now, let's talk about data. As we said in our previous cases, that a lot of the progress in machine learning and AI is because of data, right? Whether it's language or vision. But really, if you think about robot learning, we have not seen basically similar progress in data. And it's not that roboticists haven't really tried collecting data, but it's just that data collection in robotics is so hard. Often tasks are very short horizon. So you're not going to collect data for, let's say, making omelets or making paneer tikka masala, but you're just going to take very simple tasks, go here, do that kind of thing. So often data is very skill specific. It may even be platform dependent, as some of the students asking questions were pointing out. So how do we use the data to do other skills? And often this data set is very small, maybe order of minutes, and does not have the diversity. So what we really need is to think about what sort of data do we actually need? What will get it? And how would we get this? So one way to think about this is, when we collect data, what we need is, we need a mechanism to collect data which has many solutions. So the same task can have many solutions. So it can capture human ingenuity. It can capture, or it needs to capture, human dexterity, in the sense that many times we solve these tasks with very careful motions. These are very hard for machines to do. And we have to demonstrate these tasks so that a robot can eventually learn to do this. And finally, it definitely needs to be large scale. What does it mean to be large scale? In the sense that it needs to be able to do many, many, many tasks. So what have we done here? What we have really done is created a crowdsourcing tool which allows us to demonstrate dexterous manipulation, not just label it. How does it look? What it looks like is, you can use essentially a phone and your web to control the system to provide demonstrations of complex systems. And now it's not that you need to be next to the robot. You could be anywhere. You could very well be, let's say, in a conference room, at your home, in a library, controlling robots that are not co-located at all. They could be across the campus, across the city, or in tongue-in-cheek, in our case, we tried this out. This is across Atlantic and Pacific. So I was in Switzerland controlling systems back at Stanford in California, while my friend was in Hong Kong or Macau, I think, and he was controlling this stuff across Atlantic in Stanford. So it basically allows people to control real systems from practically anything. We collected a lot of data here. We collected hours and hours of data, and this was at the time 10x larger than any of the similar data sets, which is basically testament to having data will allow us to solve hard tasks in robotics. Now, the second question is, if we do have data, what do we do now? Right? So the question we are asking ourselves is, if you have data, can you learn from this data? So what is the paradigm? The paradigm goes something like this. You have a lot of data, but this time around you have a fixed data set. You can learn in an offline setting. You don't get to interact with the environment as you would usually do in a reinforcement learning setting. And then you can test your policy on the real world, right? So now it's not that people haven't tried this, but it's just that doing this on real robots is actually very hard. Practically, the thing to remember is the data will show you many ways to fail and many ways to succeed. So simple machine learning algorithms will not be able to work on this. Why? Because you are telling it that the same image is also a cat and a dog. Well, supervised learning algorithms can get confused. So what will you do? So you really think about an algorithm design, And this is like the only slide where I'll talk about detailed math or anything. But to give you an insight of like how robot learning algorithms are designed, think of a lot of data, right? So think of a lot of data of going to the airport, right? So now, perhaps where you are, you can go to the airport in multiple ways. You can take the train, you can take the bus, you can drive to the airport. At any point of time, starting from hostel, you can go to the airport in multiple ways. Now, if you train a robot to do that, showing it all of the data, it can get confused because it doesn't even know what to do. So what you can do is you can train a generative model. What is generative model? A low-level model first. What is low-level model? Low-level model is literally like how to take the next step. Right? So you can think of it like this. It's literally imitating you locally in the sense at the lowest level, it will learn to take the next step from you. But it is not learning to go to the airport from you because who knows what path you're going to take. It looks at all the data jointly to figure out what is the best way to go to the airport at a collective sense in a generative modeling sense, very much like what you see in GANs or generative models like transformers, which do generative modeling of language. So you can really think of it like this. It can think of simultaneously that there are three ways to go to the airport. This one looks the best currently. So I'm going to put my steps along this direction. So think of it like this. The high level thing is actually planning how to get to the airport. And the low level thing is basically the executor model, which is figuring out how to take the actual next step. The actual next step is what is called imitation. You're learning from the data. The high level stuff, you're basically just doing goal to goal. You're throwing away the actions. It doesn't matter how you got there. What matters is you got there. Any questions so far?
There's a question in the chat section again. So how is the penalty or the loss function decided in that dexterosity control? Because there are a lot of factors that comes into play and you can't penalty it because it missed with a certain bit of error. So like what is the penalty here in the dexterosity?
At the low level, where you can basically think of low level is, let's say, the low level goal condition controller. In that case, you can explicitly say that your model should output exactly the same thing as the data, very much like a regression problem. On the contrary, at a high level, you should output something that is distributionally equivalent. So in the sense that if it was given to you, you would not be able to tell it came from the same data set or was it generated, right? And the penalty on the high level side would be distributional equivalence. There are many ways to enforce that penalty. I'm not presuming all of you are from computer science. I'm trying to use the language that hopefully all of you will get. Okay. I'll hold the question, Piyush. I think we have 5 more minutes to go or something, right? So we may definitely not be able to go through a lot of the material, but that's fine. I think. Let me show you what this looks like, by the way, and then I'll take your question, Piyush. No problem. I'm not gonna avoid your question. Don't worry. So if you were to do simple supervised learning, so you'll take your favorite machine learning model and just like throw the data at it. So BC or behavior cloning is basically the result of that model, and this is what happens. It basically fails to do anything meaningful. Why? Because as soon as you have one error, you sort of go off track. This is why robotics is hard. Now, if we have our agent, which is basically trying to follow a high-level planner, you can actually do the full task. And in fact, this is what it looks like. So if you really think, look at that goal selection mechanism. The goal selection mechanism is predicting what you should be doing at a high level, even though it's not technically correct. Notice the can is not even attached to the arm. It doesn't matter. The low-level model figures out that for it to move the can, it will need to actually grab the can. So that brings us to the close of sort of this idea of using the data. I think because we are out of time, and I don't want to keep you here. I do want to talk to you about your questions. I would like to tell you this. Like, there are a lot of things that we can think about, but do remember one thing. If there's one thing you can remember from this talk, please let it be this. If you want to build real robots that can actually operate in real world, you will need to think about better models or better structures and representations, whether it's inductive biases or self-supervised priors, that can enable efficiency. And then collecting the right data and building causal models provides such a bias such that we can achieve this generalization. Finally, we did not talk about deployment in the interest of time, but practical considerations in robotic learning often require complementary algorithmic efforts. It's not just an applications or an engineering effort. A lot of algorithms are required just in figuring out how to put all of these algorithms on a real robot. As we build more interesting and more, let's say, expansive robots that can do things that nobody can dream of today. So with that, I think I'll leave it here as a last slide, where I give you a big picture overview. At the same time, I'm open to questions at this point. So we can use the remaining time, and happy to go over slightly if you have any more questions. So let's do that. While you guys ask questions, all of these slides, perhaps versions of these talks, are also available online, and I'll share that with Surya for him to share it with all of you.
Yeah, I would request anyone, if you have a question, please raise your hand.
Hello.
Yeah.
Yeah, hello, sir. I'm audible?
Yes, absolutely. Go ahead.
Yeah, sir. I was wondering that is it a promising is it promising that if we have more data, then we will get better results? If we have more data, then will it be?
No, it's not necessary. Quality of the data matters, right? It's like saying that getting more noisy data will result in better machine learning classifier. Not necessary.
So then, what will be the factors for classifying or sorting out your data, which will be perfect for your model? Like there may be instances that some other sensors might also be needed in a particular emergency situation or in a particular situation, but they are not required in an ongoing current normal situation. So, is there any particular factors which we have to keep in mind when we are collecting data for our model?
I think you have to think about, first of all, making sure that all of your data is not exactly the same. If it is, essentially there is marginally lower value in collecting all of the future data. Think of it like this. If you're trying to map the environment, you want to visit new places rather than going to the same route over and over and over again. So marginally, there's lower marginal value in going the same route over and over again. So it's the same way that you should visit or try to solve the problem in new ways to collect more interesting data. Now, to answer your questions about sensors, in general, you want to build a sensor suite that is multimodal, so that one of the sensors, if they fail, the other sensors can compensate. I think trying to hack the system will not necessarily solve the problem in general sense. Of course, it may feel that this is what you have done to achieve a demo, but it would not be a final fix. It is essentially a bandage. So I think, from what I understand, these sort of emergency bandages will not be general purpose solutions. Of course, sometimes everybody might use something like that in the real world. Anyways, other questions? Maybe we can have someone else other than Piyush. Piyush has definitely been very active, but anybody else? I see a number of people on the call.
Again, there's a question in the chat. So it says that we can use transfer learning for like domain transfer, use the same model for a domain transfer. But is it is the task should we proceed the task as in data centric or as in model centric? Because we can also change the model on the fly. So why do we go for as in domain transfer and we just change the data and not go for a change in the model?
Because to change the model, an engineer is needed. So eventually, when it is deployed, you want the algorithm to adapt by itself.
Okay. So is there anyone else with a question?
Aman, go ahead.
Yeah.
So I was just asking that as you shown us that we are using gyros and motion sensors of our mobile to control the robots from anywhere else in the country. So what if we create a platform and for general public so that they can just in play create the data set for us to train a specific model for that means we
That is
can.
exactly what we are doing. So I think you are you are thinking in the right direction.
Yes, sir. So it will be much easier for us as multiple users can do multiple
Indeed.
things and
Absolutely.
variation in data we can get. It will be much more.
Absolutely.
Means we can train a much more accurate model using the means a vast variety of data.
Indeed. Absolutely. I think that is the goal.
Thank you, sir.
All others, I see a lot of students. I don't know if a lot of you guys are from CS or EE, but I would like you to speak up. I know a couple of people, Piyush and Aman, have been very enthusiastic, but feel free. I think also, by the way, feel free to ask other questions that are not just about this particular talk, whether it's grad school or career or anything. I'm very glad to be here, and I can stick around to chat with you guys.
Okay. But since we have also like we are in a bit of a time crunch.
Absolutely. So I will let you guys be, and again, thank you for inviting me, and this has been wonderful interacting with all of you.
Also, I would again thank you all the participants for coming join us today, and really it has been a great pleasure for like to have with us Dr. Animesh Garg. So like a big thank you for you, sir. Also, we have for a token of appreciation, we have something a little bit of made for you. If I can share, is it visible, sir?
Oh yes, this is wonderful. I don't know who did this, but all of you are such wonderful artists. This is exceptionally well done.
Like this
Thank
was
you
actually
so
made
much.
by Sivani and from our club. So a big shout out to
Oh,
her.
thank you so much. Am I saying your name correct, Shivani? Right?
Yeah.
Thank you so much. You are a wonderful artist. May I have a picture of this? Please do
Yes,
send it to me.
sure.
And as a gratitude to you, I will make this my Twitter profile pic.
That's really our pleasure, so sure. I'll mail this to you today. So
Absolutely. Thank you so much. Thank you so much. All of you are doing a wonderful job. All of you, the organizers, and just on a signing off note, feel free to get in touch. To all of you, do not feel that I'm out of reach. If you email me and have any sort of questions, whether it's about research or career, I hope I can offer you something meaningful. With that, I think over to Surya, and I'll be signing off.
yeah,
Thank you.
I think the meet has come to an end. It's been really our pleasure, and I can't I think I'm on a circle right now, just circling my words because I really don't have a word. So yeah,
I think
thank you.
that's fine. Yeah. See you. Bye. Good day.
Aditya, Aditya, are you there? I guess we can end the meet right now. Bye.
you.